In this class, I want to have a look at a few problems on energy. One thing I want to look at is this kind of work kinetic energy theorem, which says the energy transfer from a source is equal to the amount of work done. So in a conservative system, the work done is equal to the change in kinetic energy, or the work done would be equal to the change in potential energy. Okay, so in a conservative system, the energy transfer from a source is equal to the amount of work done. So if you think about that, if we go back to the problem we looked at before when we were talking about a ball dropping from a height, if the ball is at rest up at this position, all of its energy is potential. As it drops down, all of its potential energy is changing into kinetic energy until when it hits the deck, all of its energy is kinetic. There is no more potential energy. The work done will be equal to the energy transfer, the change in kinetic energy. So the work kinetic energy theorem just relates the work to the change in kinetic energy. So the work is the change in kinetic energy. So let's have a look at this problem. A spaceship of mass 2 tons, that's 2,000 kilos, fires rockets which speed it up from 500 meters per second to 600 meters per second. Find the work done on the spaceship by the rockets. Now remember, our basic formula for work is force by distance. We don't really know the force or the distance, but we do know the change in kinetic energy, and work is the change in kinetic energy. Work will be equal to the change in kinetic energy. And the change in kinetic energy will be the final kinetic energy minus the initial kinetic energy. Kinetic energy is defined as being a half mv squared. So final kinetic energy, half mv squared, minus initial kinetic energy, half mu squared. Notice you can factor out the half m, because the m isn't changing, and what we're going to have is v squared minus u squared. So half the mass, well, the mass is 2,000 kilos, so half the mass is 1,000 kilos. And then we've got v squared minus u squared. Final velocity, well, final velocity is 600. So the square of that, 6 squared, 36, 100 squared. There's going to be 4 zeros on there, so 360,000 minus 500 squared, 5 squared, 25. And then square 100, 250,000. Okay, so we can work out what the work was that was done on the spaceship by the rocket. So it's going to be 1,000 times the difference between 360 and 250, which I think is 110,000. Okay, 1,000 times 110,000 is 110 million. And my units will be joules. So 110 million joules of work was done on this 2,000 kilogram rocket. Let's look at another problem. A painter at the top of a 10-meter ladder pulls up a 2-kilogram pot of paint by the means of a rope. Find the work done. Find the work done in order to get this going from the bottom to the top. So the work done is going to be the energy transfer. In this case, the energy transfer is going to be transferring. It's a transfer in potential energy. Okay, so the work done here is the change in potential energy. And in fact, I might just say the absolute value of the change in potential energy. So at the bottom, the potential energy, what was the potential energy at the bottom? Well, potential energy is mg, so we're talking about mg of the final height, mg times the final height minus mg times the initial height. This is going to be mg times h2 minus h1. So mg, well, m, it tells us is 2, and it's pulled 10 meters 10 meters up a ladder. So painter at the top of a ladder, he pulls a 2 kilogram pot of paint up by means of a rope from the ground. So we're talking about a final height of 10 and initial height of 0. So what we have is 20 joules of work done. Find the power output if it takes them 7 seconds. Well, we said that power is equal to work divided by the change in time. So that's 20 G over 7 joules. Okay? That works out quite nicely, I think, because 7 always works well with G. I think that works out as 27. Sorry, not joules. I'll put in the incorrect unit. Power. The units for power are, of course, watts. 27 watts. So 20 joules of work done and 27 watts of power put out in that 7 seconds. So we're transferring energy, introducing stuff. Projectiles fired from level ground at 200 meters per second. Find its speed when it is 1,000 meters in the air. Well, we know its total energy at position 1 is going to equal to its total energy at position 2 because of the principle of conservation of energy. Its total energy at position 1, well, energy is made up of potential energy and kinetic energy. And total energy at position 2 will be made up of potential and kinetic energy there as well. So first of all, it's fired from level ground. That means, you know, its height initially is 0, which means initially all of its energy is kinetic, because potential energy is defined as being mgh. The height is 0, potential energy is 0, so its kinetic energy, all of its energy is kinetic at position 1. At position 2, it's going to have potential energy because it's going to be 1,000 meters in the air, and you know, maybe it'll have kinetic energy depending on whether or not its speed will be 0. So kinetic energy, 1/2 times its mass, which is not given. We're just going to write m, times v squared. Well, v is its speed, that's 200, square of 200. And that's equal to its potential energy at position 2, which is mg times its height, 1,000, plus 1/2 times m times its final velocity squared. We're trying to find its final velocity. As always, the m's will cancel for questions of this type. Maybe I might double everything on both sides to get rid of these halves. 200 squares, well, that's going to be 2 squared 4, 100 squared. Going to give me 4 zeros, so we're going to get 40,000 is equal to 1,000 times g. I'll just take g to be 9.8, so that's going to be 9,800. And I'm actually going to double that, I'm doubling everything on both sides. So 40,000, it's going to be 2g times 1,000, so 19.6 times 1,000, so 19,600, plus v squared. And then it's just a question of solving this equation. So v squared, we're going to subtract 19,600 from both sides. So that's going to give me v squared equals, I think that's going to be 20,400. Taking the square root on both sides, v is just going to be the square root of that. I'm going to use my calculator here. Square root of 20,400 is 20 root 51. And my units would be meters per second. Okay, so there's a few little word problems on energy. So practice, practice, practice.